basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, for like my whole family. And was like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family.
What we want to look for are these perfect squares. So b to the fifth is the same thing as like b squared times b squared times b, right? Or it's the same thing as b to the fourth times b. So what I can do is I can figure out what is the square root of b to the fourth. Well, that's going to give me b squared. And then the square root of b is still going to be the square root of b. So I can simplify this. The only way that they can get out from the radical is if they're a perfect square. So this is going to be, so root 3 is still...
And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And he's like, no, I went there and I was getting, like, I was basically getting, you know, for, like, my whole family. And basically getting, you know, for like my whole family. He's like, no, I went there and I was getting, like, I was basically getting dinner for like my whole family. He's like, no, I went there and I was getting, like, I was basically getting dinner for like my whole family. He's like, no, I went there and I was getting, like, I was basically getting dinner for like my whole family. He's like, no, I went there and I was getting, like, I was basically getting dinner for like my whole family. He's like, no, I went there and I was getting, like, I was basically getting dinner for like my whole family. He's like, no, I went there and I was getting.
Okay.
No, double check before I go back to you.
Okay. So 3x squared plus 6x equals 0. So this is something called a quadratic. Okay. This is the quadratic. When you graph it, it's going to be like a U shape. It's called a parabola. And in this case, it's going to open up like this because I know there's a 3 there. And this is factorable. So I also know that it's going to look, it's going to open up and it's going to cross the x-axis in 2 spots. So it's not going to be perfectly symmetrical like that, but generally this is what it's going to look like. Okay, so the way that I can solve this, there's a few different ways that I can solve this. I can do, thank you. I could do quadratic formula, just my C value is 0. But an easier way to do this would be by factoring. So factoring is, it's related to division, but it's really just, you're rewriting it as, you're rewriting like a product as its factors. So to figure out what those factors are, you sometimes need to divide, but let me show you what I mean by this. Okay, so 3x squared and 6x. What's something that they're both divisible by? So they're both divisible by 3 and x. Okay, so we've got 3 and 6. They're both divisible by 3. How do I want to show this? Yeah. And they're both divisible by x. Now this one actually has 2 x's that I could divide by, but this one only has 1. So I can only take out the greatest common factor between these two. So in that case, it's 3 and x. Okay, now when I pull this out, I'm going to put in parentheses because then this is sort of like also like undoing distribution. Okay, so 3x squared divided by 3x is just going to be x. 6x divided by 3x is going to be 2. And equals 0 is still there. Now, what I have done here is I've got 2 things being multiplied together that equal 0. Now, what I know to be true is that in order for 2 things to multiply together to equal 0, one of those has to be 0, right? It could be 2 times 0 or 0 times 5. It's going to equal 0. Okay. So what I'm going to do is I've got 3x. So either, well, I always say either, and I should say if. If 3x equals 0, the whole thing will equal 0. If x plus 2 is the one that equals 0, the whole thing's going to equal 0. So what are the values of x that will make this whole thing equal 0? Because those are our solutions. So if I divide both sides by 3, I get x equals 0. Okay, and then here, if I subtract by 2, I get x equals negative 2. So if x is negative 2, this is going to equal 0. If x is 0, this is going to equal 0, right? Because 3 times 0 squared, 6 times 0, 0. Okay? So those would be my solutions. So that's a way to solve by factoring, right? And this is just a binomial with solving by factoring. Okay, let me see. There we go. I don't know why that's not. Sorry, guys. Hold on. Sorry. Okay. Okay, so I've got some, sorry guys, I'm catching up on the questions. Good, some people got it right on this one. Awesome. Mariana, so proofs, can you be a little bit more specific with proofs? Proofs are tricky to do in this format, but I can give you a couple of little pointers with that. Okay, but if you give me an idea, like, are you talking about like ASA? Are you talking about polygons? What are you trying to prove? What are you trying to prove? Okay. All right. So let's see. X squared minus 30 equals 195. Yeah, we can do that. Okay. So X squared. So X squared minus 30 equals 195. So this is another quadratic. Okay. This is another quadratic. Now, a lot of times when you're solving quadratics, like if you're solving by factoring, like what we just did, you have to make sure that it's equal to 0. So when you have two things that are multiplying together, they equal 0. But in this case, look, I don't have an x. We call that the linear term. I only have x squared. Okay. So what I'm going to do to solve this is I'm going to actually use my property of square roots. I'm going to add 30 to both sides, because now I've got x squared equals 225. Okay. Now x squared is a perfect square. 225 is a perfect square also, but actually that doesn't really matter when I'm solving by square roots. I can just take the square root of whatever's on this side. The important piece to solve by square roots with this is you've got to make sure that this side is a perfect square, this x squared. Or it could be 9x squared, right? But then you would probably just divide by 9. But either way. So now that I have a perfect square over here, I can do my square root of both sides. So now square root of x squared is x. Square root of 225 is plus or minus, positive or negative, 15. So my solutions are right here. So x is negative 15 or positive 15. Okay, so if it's negative 15, negative 15 squared is 225 minus 30 is 195. Positive 15 squared is 225 minus 30 is 195. Okay, so these are my two solutions for this. Now, I mean, you could solve this by factoring, but I mean, you would have to subtract this, and then you would have negative 225. So then you would end up with a difference of squares. So you would end up with x plus 15 times x minus 15 equals 0. You're still going to end up with the same thing. So when you're learning how to do the quadratic equations, when you're learning how to solve quadratic equations, one of the things that you learn and get comfortable with is knowing when to use each method. Okay, so for example, this was just the square root, right? This one that we did before was factoring, even though there was no constant term, there was no c. It's okay, we still did it with factoring. Okay, the other way that I personally love this way, which is completing the square. Okay, so completing the square, if you have something like, okay, let me make sure. I want this to do something. Actually, I want this to be, sorry guys, I'm just kind of playing around with this. Plus, let's say 35. Okay. All right, so, I don't know, equals 1. Okay. Yeah, that should be fine. Yeah, that should be fine. Okay. I'm thinking like 14 steps ahead. Okay. So looking at this one, okay, first thing I would do is you would want to see if It's factorable. Okay, so if it's factorable, you would want this to be equal to 0, so then that would be 34. 34 is 17 and 2. And that's kind of it for factors. And 17 and 2 I can't make equal 8. Now you could also go in and figure out the discriminant and stuff like that. But ultimately, I just kind of look at these like, it's not factorable. I'm going to move on to my next choice. Okay, my next thing that I'm looking at is, could I do it with a square root, right? I've got this linear term, so I can't do that. But what I do see is, since this a value is 1 and this b value is an even number, I can do something called completing the square. Okay, and I love completing the square because it feels sort of sneaky. Okay, so completing the square is where I'm going to it's related to the square root it's related to the square root method of solving. I'm going to force this side to be a perfect square. Okay, so I'm going to force this side to be a perfect square by doing this. I'm going to go ahead. I'm going to subtract 35 from this side. I know that's not always everybody's first thing to do, but I'm just going to do it for now. Okay, equals, actually I'm going to leave a little bit of space, equals negative 34. Okay, now when I look at this, I see that this is 8. This is an even number. Oh, you can definitely complete the square you can complete the square if there's a number here. You can complete the square if this is an odd number, but it's just, so annoying. So just use the quadratic formula for that. It's fine. Okay, you can, it just gets really ugly. Okay, so I'm going to take 1/2 of 8, which is 4. I'm going to square it, and that gives me 16. What I'm going to do is I'm going to make this third term here 16. And I'm going to do that by adding 16 there, but I'm also going to add 16 over here. Don't forget that whatever you do on one side, you've got to do on the other, right? So this is plus 16, and the reason I'm doing that is to just force this to be a perfect square. The reason I'm adding 16 on this side is so it's the same thing, right? So it's still equivalent. All right, so now x squared plus 8x, so negative 34 plus 16 gives me negative 18. Okay, so I can take care of that right now. X squared plus 8x plus 16, this is what's called a perfect square trinomial. Okay, it's a perfect square trinomial because half of b squared is c. So the way that I can write this is I take that half of b, and that becomes part of my binomial, and I square it right there. So x plus 4 squared, if I think about x plus 4 times x plus 4, that's going to be x squared plus 4x, which is 8x, plus 4 times 4, which is 16. So now this is a perfect square on this side. So I can take the square root of both sides. So I square root both sides and I get x plus 4 equals plus or minus square root of negative 18. Now, those of you who may just be in Algebra 1 or pre-algebra, or maybe you don't remember this, you might be thinking, no, you're not supposed to take the root of a negative number. You can't take the square root of a negative number. You can if you use imaginary numbers. And that is where we are, folks. We are in the realm of imaginary numbers because now we have this square root of a negative. Okay? So square root of negative 1 is I. That makes it the imaginary number, right? So the imaginary number is that negative. If this weren't imaginary, if this were just a root, I would still be doing the same thing, okay? So I'm going to simplify that radical in just a minute. Okay, I'm going to subtract 4. So my solutions to this one, I'm going to erase this board. Okay. So my solutions to this is x equals negative 4 plus or minus the square root of negative 18. Okay. I know I have to simplify the radical. Okay. But that was something else that somebody else asked for help with. It's simplifying the radical. So let's take a look at this root negative 18. When we're simplifying radicals, the only way to get out from underneath this radical symbol is to take that root. So what I'm looking for is I'm looking for perfect squares that make up 18. Okay, now the very first thing I need to do is I need to get that negative out. So the square root of negative 1 is I. So I've got I that comes out from there. So now I'm just looking at the root of 18. Those of you who haven't dealt with I yet, that's fine. This is still true. Okay, we'll still talk about how to simplify the root of 18. But if you have talked about I, or if you're kind of like, well, what do I like? You don't have to worry about it that much. But just keep in mind that that's only there because there was a negative under there. That's all. Okay. So now 18 is 9 times 2, right? It is also 6 times 3. It is also 1 times 18. But the important thing is that 9 is a perfect square. I can take the square root of 9, but I can't take the square root of 2, right? So the square root of 9 is 3. That can come out of the radical because it's a perfect square. I'm going to put my I there because it's still it was the negative 18. And then what's left behind is root 2. So now my actual solution, my actual x values are negative 4 plus or minus 3i root 2. And that's it. Okay. All right. Let's see. Okay, sorry guys, I went through here. All right. So can't tell if that's Reb or Rob. So the only thing so I equals the square root of negative 1. So as soon as you see a negative underneath the radical sign, you just pop an I out. Ooh, I don't like how that sounded. But you just bring the I out. And that takes out that negative. Okay? All right, let's see. Ooh, Daniel, that's good. All right, so Cool Kid Club, this is from, we went through and we were solving a quadratic through completing the square. So that's where we started and that's where we ended. Okay. Oh no, Alexis, I hope you did okay on your test. All right, so Megan over on YouTube is asking, what's the point of simplifying it? It's like simplifying a fraction or something like that. You want it to be in the simplest form because then you can look for things like common terms and stuff like that. Okay, let's see. All right, so the question with proofs, Mariana. So proofs when they are perpendicular or when they are segment bisectors. Do you mean within a triangle? Within a triangle, maybe? Geometry can be tough. And I mean, I primarily teach geometry. Joel, you're in pre-calc honors. Can you do a factoring problem? You mean like with a quadratic for factoring? Okay, let's see. All right, so Mariana was asking about proofs. Now, proofs are a little bit tricky for me to do just in this format because there's so much like writing involved and all of that. But so with a perpendicular bisector, what was it? What was it that she said? When they are perpendicular or when they are a segment bisector. Okay, so so I'm going to write that problem down and we'll do that one next. x squared plus 10x plus 15. Oh, I wrote that really sloppily. Okay, x squared plus 10x plus 15. Okay. Okay. Avion, the difference quotient. Do you mean like the rate of change on a function between 2 points? Okay. Let me write that down, and I'll do that after the I'm going to do proofs. And then I'll do that question that, was it AJ? Zoe. That Zoe put up, okay? All right. Okay. What am I doing? Oh, I'm doing the, okay, and then Kendall, I'll do quadratic and discriminant. Okay. How do I feel about calculus? I don't know. You know, calculus is like the one math level that I haven't taught at, so I don't have a deep appreciation for it. But I mean, I took 3 or 4 years of calculus, so like that's fine. It's just a lot. There's a lot that go into it. Okay. All right. Let's talk about proofs. So with perpendicular bisectors or segment bisectors, right? So Mariana was asking about doing proofs when they are perpendicular or when they are segment bisectors. So if you have something, so if we've got a triangle, and Mariana, again, I'm gonna do my best to try to help you with this. So if I've got this triangle, okay, and I'm gonna give you some given information. I'm gonna say like BC, no. I'm going to say that D is the midpoint of AC. Okay. So this is all we're going to start by giving. Okay. So D is the midpoint of AC. So all that I know is that AD equals DC. That's all that I know. I don't know anything about these angles. I don't know anything about these side lengths. I do know that BD is congruent to itself, right? If I look at this as 2 different triangles, I know that this side and this side are congruent. This side and this side are congruent. Okay? So by saying that D is the midpoint of AC, that tells me that AD is congruent to DC. Now, beyond that, there is not much else I can do just based on this information. Okay? I know it hasn't asked me to prove anything. I get that. But also, I don't know anything else. I can't prove that these 2 triangles are congruent because I don't have any information about the angles. Okay? Now, if I am told that... if I am also told that AB is congruent to BC. Now that opens up some doors. Okay? Because now I know that triangle ABC is an isosceles triangle because these 2 sides are the same. Could it be equilateral? Sure, but I don't know what AD and DC are, but I know it's at least isosceles, which means that these 2 sides are congruent. Now, congruent sides, congruent angles. So this angle here is congruent to this one here. Okay. So since this is the midpoint, and since these are congruent, and also these two angles are congruent, what that means is that since the distance of this point to both of these sides is congruent, I can conclude that BD is a perpendicular bisector. Of AC. Because by definition, it needs to be that the distance, so if this is through the midpoint, we know it's already a bisector, right? The fact that it's right here, okay, the fact that it's passing through that point right there means that it's the perpendicular bisector. Okay. Now we could also, if this were a question about showing that these triangles are congruent, that would be kind of a different story that we were telling, right? But the question was talking about more of like perpendicular bisectors and segment bisectors. Okay. So if we were going through to figure out, so, okay, guys, everybody in the chat is missing what the question was. Okay. I'm not trying to prove if these two triangles are congruent. What I'm trying to prove is that BD is a perpendicular bisector. Okay, that's what I was trying to prove. Yes, we could prove that these triangles are congruent. Yes, that wasn't the question. Okay, so the question was about perpendicular bisectors. Okay, so could I go on to explain this and show that these two are congruent? Yes, I could do this by any number of ways, right? I could do SAS. I could do side, side, side. I can't necessarily, well, now that I've established this, I could do hypotenuse leg now. But I have to establish first, I had to establish that it was a perpendicular line. Okay, so you can't just jump into hypotenuse leg without knowing that it is, that it's a right triangle. Okay, so a perpendicular bisector is a line that goes through the midpoint at a perpendicular angle. Now, if it also passes through the vertex here, it's going to be the same distance from these two sides. So when you're writing proofs in geometry, and this is why I usually don't do proofs on this channel because it gets really difficult and really convoluted very quickly. But there's a lot of, there's typically a few different ways that you can go about things. Some ways will be more efficient than others. But if you're trying to prove that it's a perpendicular bisector, the big thing that I would say is for when you're writing proofs, make sure you really know your definitions, right? Really know your definitions, and make sure you understand like what I call these loaded terms, like perpendicular bisector, right? It means all of these things. It means that it's 90 degrees. It means that these two are equal. It also means that these two have to be equal if it's passing through that point. Okay, now if it's not passing through the point, it could still be a perpendicular bisector, but it's just not this, the rest of this stuff isn't going to be true. Okay. All right. So let's move back over to some quadratics and some algebra 2 material. So we had somebody that put in this expression plus 10x plus 15. Okay. So was that Zoe? I think that was Zoe. That was asking for this one. Make sure I got this written down correctly. Oh, somebody, let's see. Alicia asked for imaginary square roots. I just went through those. Okay. Oh, AC method. Yes. All right. Zoe, I don't know if you're here still or not. I can't see it. I can't see you. So maybe if she's not in here, because I'm not sure if I wrote this down correctly or not. Not sure if she wrote this down correctly or not. Okay. Okay, so we'll come back to that if we need to. Oh, what is this that I jotted down? So I'm trying to write this all down. Can we also do when the given has line A, B? Yeah, so if you're told that the given is that it's perpendicular, what you're looking for then, so Mariana, let me look at, so if you were told, so what you're looking for is if it's a perpendicular bisector, that has to be 90 degrees and these have to be congruent. It's got to be the midpoint. So those are the two things that you're looking for, is if it's perpendicular and it's a midpoint, then you can do that. But the other thing that you can look for is if these two sides are also given, or you're able to determine that they are congruent, then that means that you've got a perpendicular bisector. Okay. All right. Oh, so you are here. Okay, perfect. So I did write that down correctly. And do you just need to simplify it, or are we solving it? Or are we graphing it? What are we doing? Grab. Any teachers out there know that I'm a little particular about my dry erase markers, and these ones are just going through the ringer. Okay, so you're solving it. So I just had, so you've got 4x minus 1 over x squared plus 10x plus 15. And what does that equal? Oh, sorry. It equals 0. Okay. All right. So I'm going to put that up there for a little bit. Okay, and those of you kind of following along at home, want to try your hand at this. I'll give you guys a minute or two to try it out. One week I should have a guest teacher on here that's my colleague that teaches calculus. I think he'd have a lot of fun doing this. Okay, so looking at this, right, if this is going to equal 0, okay, the only way that this one is going to equal 0 is if you do 4x minus 1 equals 0, okay? But this one brings up a really good point, because you also cannot have any values of x that are going to make it 0 down here, okay? So 4x minus 1 equals 0, right? That would be x equals 1/4, right? If x equals 1/4, because 4x minus 1 equals 0, so you would add 1, 4x equals 1, so x equals 1/4, okay? So if you have x equals 1/4, okay, great, that's going to be 0 because you know that top is going to be 0. Now the other part of this, though, is what's on the bottom. This cannot equal 0. So there's got to be at least one more value that x can't be. Okay, now if this is part of a function, right, that's going to be a little bit different because these are going to be like, you know, like it gets into the whole thing about like holes and asymptotes and all that kind of stuff. Okay. But so let's figure out the values of that x cannot be. Okay. So x squared plus 10x, we want to figure out what values of x are going to make the bottom of this 0, because those are the ones that we can't use, right? Okay, so x squared plus 10x plus 15, is that factorable? Let's see, we've got 3 and 5, no. Okay, so, ooh, we could complete the square on this one, right? We could complete the square on this one. So let's do that. Let's do x squared plus 10x equals negative 15. Okay, I just subtracted 15. Half of 10 is 5. Okay. 5 squared is 25. But I can't just add 25 over there. I've got to add it on both sides. So I've got 10. So now I've got x plus 5 squared equals 10. So if I square root both sides, I get x plus 5 equals plus or minus root 10. Root 10 can't be simplified because it's not made up by any perfect squares. So I would subtract 5 and I get x equals negative 5 plus or minus square root 10. So these two answers, or these two values, negative 5 plus or minus, or negative 5 plus root 10 and negative 5 minus root 10, these are what x cannot equal to. And the reason it cannot equal this is because that would make it 0 on the bottom, so we can't have that happen. Okay, so we've got one solution where x equals 1/4, right? But again, I'm not entirely sure what the context is of this here. So x would be 1/4, which makes it 0. But also another part, if you had your solution set, x cannot be negative 5 plus or minus root 10. So that would be sort of like my second kind of like suggestion or answer, I guess. But again, it kind of depends on if this was coming from a function, right? Are you trying to just solve the function, right? It would be a little bit. I would recommend if you have a graphing calculator or you have Desmos, graph that and see what happens with it. Okay. All right. Okay. I wrote down here quad D-I-S-C. Quadratics discount? I don't know what that is. All right, so an integral test, and I see a lot of questions about like shell method, things like that. That's a little beyond what we usually get into on this channel, but that's okay, because if you still have a specific question, you can put it into the chat. And we've got Avian, who's been waiting very patiently for difference quotient. Okay, let me find a good, let's see. Okay, so the difference quotient, let's see. Avian, do you have a specific, hold on. Oh my God, I've already filled up so many boards. Avian, do you have a specific question for this, or just kind of in general, like difference quotient? Just in general, okay. All right, let me pull up, let me find some, Okay, so basically the difference quotient is really just looking at the difference or the average rate of change kind of over an interval. Okay. So if you have, let's see, I'm trying to find a good example. And this is getting into like pre-calc, right? But okay, so if we have we have a parabola, right? And then you've got a line. It's going to look something like this. Okay, so we've got this point and this point. Okay. All right. Okay. So here, what we've got is this point right here is going to be like your x and f of x, right? Or your x and your y, right? And then this one here, okay, we've got this, I'm trying to think of the best way to show this. So this is where my x is, my original x. And then this is where my other x is, right? For like my second part, this is like my range, right? That I'm trying to figure out. So this distance here between the x values is h. Okay. So this one, this interval, or I'm sorry, this point here would be x plus h, and then f of x plus h. Right? So whatever change this is kind of going through. Okay, however much you're increasing. Okay. All right, I see questions about Pythagorean theorem, and I'll put that on there. Okay. Okay. So then that's the wrong one. So the difference quotient is really just looking for the difference between these two, okay? And it's the secant line, right? So you can get into limits and things like that. But what you're really looking for, I know, Avion, you were kind of just asking for like a general thing, right? So what you're going to be looking for is that that difference here in the average rate of change. Sorry, hold on. I've got 14 different things going on. So if you take the f of x plus h minus f of x over h, and then you can get into some limits and some derivatives and things like that. But that's kind of as deep as I can really go. Oh my gosh. Okay. Alex, thank you for jumping in on that. All right. That's really hard for me to read on there. Okay. Okay. All right, so Pythagorean theorem. Let's move on to Pythagorean theorem. So with the Pythagorean theorem, what we've got is we've got right triangles. Okay. Yeah, Avian, I'm having a hard time understanding what the question is that you're asking. I don't know. I thought you were just kind of asking for a general overview of what it really is. Okay. Yeah, okay. So let's go to Pythagorean theorem. Let's get back. Let's get out of the calculus realm. Okay, so Pythagorean theorem is anytime you have a right triangle, you have two legs and you have the hypotenuse. Okay, so the legs are what make up the right angle. Okay, the hypotenuse is going to be the longest side because it's across from the largest angle, which is 90 degrees. Okay, so I can use my Pythagorean theorem. I know it's a squared plus b squared equals c squared, but the problem with that is that you don't always have a, b, and c. Those aren't always what you have. So if you square the legs, whatever letter they are, you're going to get the square of the hypotenuse when you add those together. Okay, so that's going to always be true. So if I've got a right triangle, and this side is 4 and this side is 9, okay, what is my hypotenuse? Okay, so we've got 4. I'm going to write these so they're not crooked like the triangle. So this is 4, this is 9. Obviously not drawn to scale, I know. Okay, but we have 4 and 9, and so how would we figure out what the hypotenuse is? And we're not going to round it, we're going to simplify the radical. Okay, so we're getting root 97. Okay, flipbo. This is algebra 1 right here, buddy. So Angelica, the hypotenuse is always going to be across from the right angle. So it could be wherever. It just depends on the orientation of the triangle. Like it could be flipped over, it could be turned around, whatever. Okay. So flippo. The Pythagorean theorem never goes away. So you may learn it in 8th grade math, but this is algebra 1 too. This is everywhere. Okay. So what I'm going to do is my legs are going to make my right angle in my right triangle. So I've got 4 squared plus 9 squared is going to equal h squared. 4 squared is 16 because it's 4 times 4. 9 squared is 81 because it's 9 times 9. So 16 plus 81 is 97, which is h squared. So then h by itself is going to be square root of 97. Now, if we were to, let's see, we can't really simplify that. Is 97 a prime number? It might be. Yeah. That is simplified as far as it goes. But if you were to if your teacher were asking you to round it to the nearest tenth or so, it would be 9.9, something high, something close to 10, because the square root of 100 is 10. So square root of 97 is going to be 9 point something high. Okay. So then, but what if we didn't have both legs? What if we had the hypotenuse? I'm going to draw this one kind of backwards, sort of. Okay, so now on this one, we have the hypotenuse, but we're missing one of the legs. All right, so here we've got the hypotenuse. So now the way that we're still going to plug it in, right? So we've got our leg squared plus our other leg squared, which is x in this case, and then the hypotenuse squared. So I have 16 plus x squared equals 144. So then I subtract 16 from both sides. And I get x squared equals, so that's 8, that's 24, 128. Is that right? 128, yeah. Okay. So x squared is 128. So x is going to be the square root of 128. I don't want to take the square root before I've got all the numbers on one side. Okay, so square root of 128. So 128 is divisible by 4. Okay. So it is divisible by 4. So 128 divided by 4. And the reason that's important is because 4 is a perfect square. So that's going to give me 32, right? Okay, so 32 is divisible by 16, right? So actually, 64 times 2. 128 is 64 times 2. So 64 is a perfect square. So that can come out. So that's going to be 8, because the square root of 64 is 8. And 2 is left behind. So my value of that leg as a simplified radical is 8 root 2. Now, if I had to round that, let's see, probably, 10 point something, 10.5-ish. Probably because 10 squared is 100. 11 squared, oh no, wait. Oh my gosh, I was thinking 12 squared. So it's going to be close to 11. Okay, I just skipped over 11 apparently. Doesn't exist. Okay, so that would be about 11 point something low. Would be close. Okay. All right. 11.31. Excellent. Thank you. Somebody with a calculator over there. Okay. Let's see. Okay. All right, let's do one last round. Let's talk about function notation, because that's something that is always a bit tricky for students, and it's really actually quite straightforward. Okay, so function notation is when you see something like f of x. So f of x equals 2x plus 1, okay? So what that means, that f means that it's a function of x. So this is my input. This is whatever I'm putting in here. And what it's going to spit out is after it goes through the function, which in this case, the function is times 2 plus 1. Okay? So f of 2, my input is now 2. My whole function stays the same. The only thing that changes is that my x is now 2. So that would be 5. So f of 3 would be 2 times 3 plus 1, which is 7. F of a would be 2a plus 1. I can't simplify that, right? F of x plus 5 is going to be 2 times x plus 5 plus 1, which is going to be, let's see, 2x plus 10 plus 1, so that's 2x plus 11. Okay, so function notation is really straightforward. It's just whatever you get out after whatever you've put in. Okay, it's whatever you get out. Now, f of x, when you're graphing, f of x is the same thing as y. It's the output. Okay, so, yeah, because y is a function of x, or f of x. Exactly. Okay, so this one here, so f of x, This function notation, you're seeing it earlier and earlier in middle school, which I think is really grand and great because it is something that throws a lot of students off, and it's not super complicated. It's not super complex. Okay. Again, it's a simple, straightforward thing, but simple doesn't mean it's easy, right? Complex doesn't mean it's too hard or too challenging. Okay, but simple is simple and complex is complex, and that's all there is to it. Okay, all right, guys, that is about it for me because it has been quite a week. But I will. Oh, we'll probably not. Well, we might be live at some point next week, maybe towards the early end of the week. For those of you who are still in school, good luck on all your math tests tomorrow. Sorry we can't do everything, but we got to a lot of good stuff tonight. So have a great night and a very happy Thanksgiving. All right. Goodbye.
There's some